We've come a far way with all these physics labs, but the day to end it has finally come. But let's end it strong with Lab 5, Faraday's Law. Well, what is this lab all about? Well, the purpose is to study magnetic induction and eddy currents by analyzing observational data of a bar magnet falling through an aluminum tube and then comparing that with a computational model. Well, for the computational model, we're going to be using GlowScript to simulate everything, where our system will be the bar magnet and aluminum tube, and the surroundings will be everything else. And here's just a quick preview of both times. Alright, now for the big physics concepts. First, we'll use Faraday's law, which states that a changing magnetic field creates a voltage in a loop that follows this formula. Next up is the Biot-Savart law, which tells us that a steady current creates a magnetic field around it, whose strength follows this relationship. Lastly, we need to use Newton's laws, specifically the second law, which states that the net external force on a system equals its change in momentum over time, and the third, which is just the action-reaction law. For this lab, I dropped a bar magnet in an aluminum tube and measured the amount of time it took until it left the tube. As you can see in the picture and video on the left, there is an upward magnetic force created by the induced currents in the tube that slows the magnet down. This phenomenon is exactly what I'm trying to observe and simulate in this experiment. Now to do so, I need to make a few assumptions, such as air resistance being negligible, the bar magnet acting as a magnetic dipole, and the only forces present are the magnetic and gravitational forces. On the left, I have listed the dimensions and properties of the aluminum tube and bar magnet that I used in my experiment. The table on the right displays the change in time for the bar magnet to enter and then leave the tube for 5 different trials, with the average fall time being about 1.254 seconds. Now it's time for the computational model. First up, I went in and listed all my initial conditions, such as the physical constants and the tube and magnet properties. The big code on the right calculates the magnetic field of the bar magnet and the change in magnetic flux that it produces. Here's the meaty part of the code, where I declare all the different forces acting on the magnet, which in this case is the magnetic force acting upwards and the gravitational force acting downwards. Adding these two up gives us the net force, which I then use to update the velocity and position of the bar magnet. With all that code out the way, we're finally able to create a visualization and graph of the motion of the bar magnet as it falls. In the graph, we see that as the magnet enters and leaves the tube, that the gravitational force is greater than the opposing magnetic force, and this causes the magnet to accelerate. However, in the middle of the tube, the two forces seem to balance each other out, and this causes the magnet to travel at a constant velocity. So how can we go about interpreting this simulation? Well, here's a couple of questions we can consider. First, which color corresponds to the clockwise and counterclockwise current of the animation we saw in the previous slide? Well, by using Lenz's law, we see that red is counterclockwise and blue is clockwise. Next up, what happens if we were to flip the magnet? Well, the magnet will fall just as before, but the direction of the two currents would be flipped. Next, how do the real world and computational changes in time compare to each other? Well, based on the data, the computational model was slightly shorter, but accounting for human errors and air resistance can definitely increase the accuracy of our results. And finally, what does the shape of the plot tell us about the forces acting on the bar magnet? Well, as stated before, the gravitational force is greater than the magnetic force when entering and exiting the tube, but is equal within. Since we had to make a few assumptions in this lab, we are bound to make some errors, such as outside forces like friction and air resistance slowing the magnet down, and also some human error in not precisely starting and stopping the stopwatch, all of which could alter our data. To end this lab off, we're going to dive a bit deeper into the results. First up, what if the tube resistivity were close to zero? How would the magnet dynamics change? Well, from Ohm's law, V equals IR, decreasing the resistance would increase the induced currents, and this would produce a stronger opposing magnetic field, and thus this would slow the magnet even more. Next, what if slots or holes were cut into the tube? How would this affect the ring current model? Well, there would be less current rings within the tube, and this would overall produce a weaker opposing magnetic field and cause the magnet to fall even faster. And just like that, our physics lab journey has come to an end. As always, thank you all so much for your attention, and I hope these labs have come to some use. Until our next endeavor, peace.